Most of the graphs that we've studied so far have been something called smooth continuous curves. For example, if I were to draw a linear graph, just a straight line, and you were to put your pencil on that line, you could follow this line forever up and forever down without picking up your pencil. Or the other function that we spent a lot of time studying in Algebra 2 was the quadratic function. If you put your pencil on the U-shaped curve, you could follow it both directions and never have to pick your pencil up. But however, there are these other types of functions that have something called a discontinuity, where you would have to pick your pencil up and move it. And we're going to talk about these three different types of discontinuous functions. The type of discontinuity is called an infinite discontinuity. In Algebra 2, we talked about graphs with something called an asymptote. Sometimes a graph gets closer and closer to a vertical or a horizontal line, but it never really touches or crosses that line. There is an asymptote in the equation of y equals 1 over x squared at x equals 0. That means there's a vertical line here that graph never touches or crosses. The reason there's an asymptote there is because I can't plug 0 into that equation, because then I get 1 over 0 squared, and you can't have 0 in the denominator of a fraction. We call that undefined. So it creates what we call an infinite discontinuity. You infinitely get closer and closer to that line, but you're never going to touch it or cross it. And you would have to pick your pencil up if you were following one half of the curve in order to move to the other half of the curve. The second type of discontinuity is called a jump discontinuity. Remember when we graphed piecewise functions? Those were the ones where we would have graphs that had restricted domains, and so we would cut part of them off. Well, sometimes what happens is two ends of a graph will approach the same x value, but they have different y values, and they're not connected, in which case there's this gap in the graph. So they both ends of the graph here end at x equals 1, but they don't connect. And because they don't connect, that gap causes something called a jump discontinuity. The last type of discontinuity is called a point discontinuity. In Algebra 2, we talked about something called rational expressions. So this is the graph of x squared minus x minus 2 over x minus 2. And I want you to notice that the graph is just a straight line, but there's a little hole in the graph. Now, the reason this is the equation of a graph is because if you factor the numerator, you'll notice that there's a common factor in both the numerator and the denominator, and they cancel. So that line is really just the graph of y equals x plus 1, which is linear. Except that the original equation, what happens if you plug 2 into the denominator? You would get 0, and you can't have 0 in the denominator. So there's only one point where the graph does not exist, and we call that a point discontinuity. Let's talk about how you determine whether a function is continuous or not at a given value. Now, just because we give you an x value doesn't mean that the function is not discontinuous. All we care about is if it's continuous at a certain x value. Now, you don't need to graph this to determine it. So basically what we're going to do in the first problem is we're going to plug in -3 for x. So y is equal to -3 minus 5 over -3 plus 3, which is -8 over 0, which is undefined, which means it's not continuous at that point. As a matter of fact, that was, one of our discontinuities. In the second one, we give you a piecewise function, and you don't even have to graph it. we want to determine if -2 is a point where this function is continuous or discontinuous. If it's continuous, when I plug in -2 into both equations, the output would be the same because they'd be approaching the same value. So if I plug in -2 into the first equation, I get 6. If I plug in -2 into the second equation, I get -6. That means that at the x value of -2, those y values have approached completely different numbers, in which case it is not continuous. In Algebra 2, when we started studying polynomials, one of the things we talked about was something called end behavior. Sometimes we want to know where a function is headed as x gets bigger or as x gets smaller. Now, the way it was described to you in Algebra 2 may be the way that I'm about to do it, or it may have been described a little bit differently. We look at a graph from two sides. So let's look at graph A. I'm going to draw this red line down the middle on the y-axis. Everything to the right of that graph is the positive x-axis. Well, remember that x gets bigger forever and ever? So we're going to write x approaches infinity. And then on the left-hand side of the graph is the negative x direction. So on that side, we're going to write x approaches negative infinity. What we want to do is we want to determine where the y values are going. And that's going to be different on every graph. So in graph A, if you follow the curve, first it goes down, but then the graph goes up, and unless you see any more of the graph, you just assume that it continues going in that direction forever. Well, up is the positive y direction, and since it goes up forever, we say y approaches infinity, or positive infinity, some people write. On the left-hand side of the graph, if you follow the curve, it goes up, but then it comes down, and you assume that it goes down forever. So we say that it approaches negative infinity. In every graph, if you cut the graph in half by putting a line down the y-axis, the right-hand side is always x approaches infinity, and the left-hand side is always x approaches negative infinity. All we want to determine is where are the y values going. So let's start on the right-hand side of the graph. It goes up, but then it goes down forever. So y is going to negative infinity. On the left-hand side of the graph, it goes up, and then it goes down forever. Y is also going to negative infinity. We'll talk about in a few moments how you're going to know if the two sides of the graph go in opposite directions, or if they go in the same direction. The next one, C, I'm going to cut it in half. I'm going to write x approaches infinity on the right. I'm going to write x approaches negative infinity on the left. On the right-hand side, the graph seems to be going down. That's negative infinity. And on the left-hand side, the graph appears to be going up. And that's positive infinity. In the last graph, D, this side is x approaches infinity. This side is x approaches negative infinity. Both sides of the graph are going up. So y must be going to positive infinity on both sides. So let's actually look at some graphs of polynomials and describe their end behavior. So first we're going to start with y equals 4x to the fifth plus 2x to the fourth minus 3x minus 1. Now in order to do this, I'm going to plug this into my graphing calculator and I'm going to look at the graph. And I get this. So remember, in order to do end behavior, the right-hand side of the graph is the side where x approaches positive infinity, and the left-hand side of the graph is the side where x approaches negative infinity. What we want to do is determine where the y values are going. So on the right-hand side of the graph, you'll notice the graph is going up. So y is approaching positive infinity. And on the left-hand side of the graph, you'll notice that the graph is going down. So y is approaching negative infinity. Now let's look at y equals negative x to the 6th plus x to the 4th minus 5x squared plus 4. So when I graph that on my calculator, you get this graph, which I guess is a little bit dark on the screen, but if you have it on your calculator, you'll see that on the right-hand side, the graph is just going down, so y is approaching negative infinity. And on the left-hand side of the graph, you'll notice the graph is going down, so y is again approaching negative infinity. Now, I can tell you without graphing if a polynomial, or what the polynomial's end behavior is going to be. So I will tell you that anything that is positive x to the 3rd, or positive x to the 5th, or positive x to the 7th, anything where the leading coefficient is positive and odd, I know the end behavior will always be positive infinity on the positive x side, and it's going to be negative infinity on the negative x side. If it's a negative x to the 3rd, or negative x to the 5th, or negative x to the 7th, the graph will have this general shape. On the positive x side, the y values will be going down, and on the negative x side, the y values will be going up. So notice that when the power is odd, and I mean the biggest exponent of x, one end of the graph will go up, and the other end will go down. And which side it is depends on if the leading coefficient is positive or negative. How about positive? How about even numbers? This was like an x to the 4th polynomial, and x squared we know looks like this. All of our even powered polynomials, both ends will either be going up or both ends will be going down, depending on if the leading coefficient is positive or negative. So if the leading coefficient is positive, then both ends, their y values will be approaching positive infinity. But if it's negative, for example, negative x to the 4th, both ends are going down, so y will approach negative infinity on both sides. And it doesn't matter if it's negative x to the 4th or negative x squared, or negative x to the 6th, or negative x to the 8th. The last thing that we're going to talk about is something called intervals of increasing and decreasing. If you read a graph from left to right, there are points where the graph changes its direction. So in this picture on the screen, from left to right, since my pencil is going down, we call that an interval of decreasing. But then at this point here, the graph changes direction, and now my pen is going up. So we call that an interval of increasing. So on this particular picture, we're actually going to find how to determine where a graph is increasing and decreasing and how to write the intervals. So I have a very formulaic way for how I do these problems. The first thing I do is I read the graph from left to right. So first, the graph is decreasing until it hits this point at negative 1, 2. So I write decreasing. And then it changes direction, and from negative 1, 2 to 0, 5, it's increasing. And then from 0, 5 down to 1, 2, it's decreasing again because it's going down. And then at 1, 2, up forever, it's increasing. What I'm going to do now is next to these words, I'm going to write little inequalities to explain what was going on. I'm going to get rid of that for a second. All right, so the first unit that was decreasing, from that x value of negative 1 all the way to the left, it's decreasing. And so we're going to say that the interval is decreasing when x is less than negative 1. And then from x is negative 1 to x is 0, it's increasing. So we're going to write from negative 1 until 0. And I just wrote that as a compound inequality. Then from 0 until x is positive 1, the graph was decreasing. And then when x is 1, up forever, the graph is increasing again. So notice that the two ends of the graph have a single inequality, and the ones in the middle were those compound inequalities. So let's do another problem where we're going to determine the intervals for which the graph of y equals 2 times the absolute value of x minus 3 squared plus 1 is increasing and decreasing. So first we're going to plug it into our calculator. Please type it in as is. Make sure you use the parentheses. Don't forget the absolute value of x. And then this is the graph that we see. So let's figure out how many intervals there are. So the graph is decreasing until here. So it's decreasing. And then it starts increasing up to some point up here. And then it starts decreasing again. And then it increases forever. Now, the way this is going to work is the first interval is always going to be x is less than some number. Well, less than what is the question? Well, I want you to notice that the x value appears to be at about negative 1.5. So we'll just go with that. The next interval will start at negative 1.5, and it ends at this x value, which is clearly at 0. The next interval will start at 0 and end here, which appears to be positive 1.5. And the last interval will always be x is greater than that last x value. So if there are only two intervals of increasing and decreasing, then they would look like this. One of them would say x is less than a number, and one would say x is greater than a number. If there's 3 or more intervals of increasing and decreasing, the intervals in the center will always be compound inequalities. And I want you to notice that these two numbers are the same. These two numbers are the same. These two numbers are the same. And it always works that way. And that is continuity and end behavior.